Okay, we'll wait for a few minutes for others to join. Okay, I think we can start. So welcome everyone to week 3 tutorial for the course IC engine and gas turbine. Okay. Am I audible to everyone? Can someone unmute and confirm me?
Yes, sir, it's audible.
Okay, okay. Thank you, Santosh.
Thank you.
Great. All right. So I hope everyone is regular to the lecture videos by the professor and regular to the assignments as well as those who have missed any of the tutorial sessions so far. I hope they have again visited the recordings, tutorial recordings, which we have done in past 2 weeks. And I expect that everyone is getting the mail from the NPTL team where they are telling you about basically the link sheet is there where all the recordings links are available, as well as the Google Drive link for the PDF of the notes. And those who are not able to access the sheet still, as I told multiple times. So all these recordings are on my YouTube channel as well. And the name of my YouTube channel is NPTEL with Varnit. And under the playlist section for this current course, you will see for each video description the Google Drive link for the PDF notes as well. So you can watch the recordings if you have missed and check out the PDF of the notes. All right. So let me share my screen. I hope my screen is visible now. Yeah, I can see that. Okay. Art. Yeah, great. And my video is also visible. I saw in my previous recording that my initial part of the video was not showing up. I don't know why, but I switched on my camera that time. But in later half, it was accessible. No issues. So if you feel any doubt, any query at any point of the time during the session, you can just uh, like unmute yourself and ask me or want to write in the chat. But I'll prefer if you unmute and interact with me. That will be a much better scenario for me as well. Or if you have any doubts, don't hesitate to ask them. All right. So in the last tutorial, we finished with the air standard efficiencies for the auto and diesel cycle. Okay. Especially the diesel cycle one. And we did a numerical as well for the auto cycle. Today we'll start with the concept of mean effective pressure. What do we mean by mean effective pressure? Then we'll do some numericals and let's see. how the time proceeds. Okay, so let me write it down. The topic: mean effective pressure. Okay, I hope that my whatever I'm writing on the screen is visible. Can anyone confirm? My video and audio are also coming. Everything is perfect. Please, any one
Yes,
of
sir.
you can. Okay, thank you so much. So, what do we mean by a mean effective pressure? So, a mean effective pressure is nothing but a mathematical technique to determine the imaginary pressure which will remain constant all around throughout the cycle to give us the same work done like the work done has been done by an actual cycle and for the same volume change Let me write it first, then term by term I'll explain through a pictorial representation as well. So it is a mathematical technique to determine imaginary pressure which will remain constant to give us same work done like work done of actual cycle for same volume change. For same volume change. So what do I mean that? First of all, it's a mathematical term. There is no physical significance to it. Okay, it's a mathematical tool which we are using, mathematical technique. Okay, to determine imaginary pressure. So pressure is imaginary. We are assuming that, which will remain constant throughout. Okay, to give us a same work done, like work done of an actual cycle for same volume change. For same volume change. So suppose, let us say, for an example, we have the plot of an Otto cycle. Okay, let me draw it once again. We have pressure volume plot of Otto cycle. I hope everyone remembers how it looked like. Okay, so this is a process 1 to 2 isentropic compression, 2 to 3 heat addition at constant volume, 3 to 4 isentropic expansion, and 4 to 1 heat addition at heat addition at what? Heat addition at heat rejection at, sorry, my bad, heat rejection at constant volume. Okay, so what is the net work done of the cycle? We say that area under this complete graph, the net cycle is your net work done. This is your work done. Okay, the net work done by the cycle. If I say from the definition, it is a mathematical technique to determine imaginary pressure. So it will be an imaginary pressure which is constant. Let me again redraw the axis. I want to make a bigger axis. Okay, this. Okay, this I think is much bigger. I think this will work. Huh? Yeah. So this is a pressure volume plot. A constant pressure. So first thing is a constant pressure. If I'm saying it's a constant pressure, so that means suppose constant pressure. The pressure is going to remain constant. Let me draw a what tool? Constant pressure. Constant pressure, which give us same amount of the work done. So whatever work done I've got from the Otto cycle, whatever work I've got from the Otto cycle, it will give me the same amount of the work done. And work done come from area under the PV plot. because work done from thermodynamics is for a closed system is PdV. Okay, PdV. So work done, same work done for same volume change. So for an Otto cycle, what is the volume change? If you see, for an Otto cycle, the volume changes from this to this. Okay, this to this. So that means the volume change for this mathematical expression will also belong from this to this. So let us write here. Let us use some another color. So this was your swept volume overall, Vs swept. So again, this will also be the mathematical expression will also be, which is a constant pressure area under the graph, which will produce same amount of work for the same volume displaced. That is your swept volume displaced. So what can I say that? I can say that if I take this color, so this will be my complete region till here, till here. So this is a mean effective pressure. So this pressure I can say as PM, PM, P subscript M, mean effective pressure. So a constant pressure which gives same amount of the work done. So this work done, if I say this work done, final work done is this much. Work done by mean effective pressure, work done M. This work done and work done M will be same. Work done is equal to work done M. Okay, both the work done will be same. The swept volume is same from 1 to 2 point for both of them, and the pressure is constant. It's a constant horizontal line. Okay, so this is the meaning of a mean effective pressure. It's a mathematical technique to determine imaginary pressure. Mean effective pressure is an imaginary pressure. PM is an imaginary pressure which is remaining constant. Our horizontal line is there. That give us same work done. So work done and work done under subscript M will be same for same as the actual cycle for same volume change. So swept volume from 1 to 2 is also same. Okay. So how we can write it mathematically now? That means if I say I'll use subscript this side. So I can say this work done is nothing but PM into V swept is equal to work done by the actual cycle. Work done by the... Any doubts? Anyone has unmuted? So this is net. So I can write here net, here also net. So work done net is nothing but your work done by the actual cycle, and work done M is nothing but your work done by the imaginary cycle, that is your for the mean effective pressure, which is a constant value. Okay. So this is our final expression for the mean.
Excuse me, sir, you are not audible. Sir, you had muted yourself.
Am I audible now? Hello.
Yes, sir.
Now I'm okay. Okay. So what was the last thing which you heard? Can you please tell me? Were you able to understand this box PM into VS?
Yes, sir.
Okay.
Till that
Okay.
has told.
Okay. Thank you. Thank you, Sangha. So I was saying that PM.
Sir,
This. Yes. Yes. Please ask.
what is I understand by PM? It's mean effective pressure. What is mean by VS?
Swept volume. This swept volume.
Swept volume.
Yeah. Yes. We made this in the
Okay,
last tutorial as well. Yeah. So PM into
thank you,
VS
sir.
is so work done by the mean effective pressure and work done by the net Otto cycle or the actual cycle are equal. So mean effective pressure will be pressure into change in the volume, that is your swept volume, and pressure is mean effective, that is an imaginary constant pressure, is equal to the net work done by the actual cycle. Okay, so what we can say that if more the mean effective pressure for the same swept volume, that means more the work done we are able to achieve. So more the power is that of an engine. Okay, so when we are comparing between two different engines, suppose if I say I have a mean effective pressure, one engine is having a mean effective pressure of 10 bars. I'm taking just an example, and another engine is having a mean effective pressure of 15 bars for the same volume change. So which engine is more powerful? Which engine will be more powerful? Can anyone tell me? The pressure, the higher the pressure, if higher the pressure for the same swept volume, the work done for this cycle will be much higher. Okay, so work done for a higher mean effective pressure will be higher compared to a lower mean effective pressure for the same volume change. Okay, is it clear or any doubts? I'll write this note. More the PM, for same swept volume, for same swept volume, this implies more the work done or power obtained for comparison between engines. Okay, I hope this is clear. So we can proceed to a question. Okay, a numerical. Any doubts in this, or should I proceed? If you have any doubts, please ask. If no doubts, we can proceed. Okay, so the question is, in spark ignition engine, joint. Oh. In spark ignition engine, which is working on Otto cycle, compression ratio is 5.5. 5.5. Work output per cycle is equal to 23.625 into 10 to the power of 5 into Vc, that is your clearance volume, joules. Okay, this is your work done, where Vc is the clearance volume in meter cube. Determine the mean effective pressure. Okay, you have to do this question. Take few minutes and do the question, please. I'll give you chance. Whosoever get the answers, please tell me what is the answer you get. It's a very simple question. Please solve this question. I'm here in the class itself. Anyone is able to do? Answer, please.
Sir, 2 seconds.
Okay.
Sir, 5.25 bar.
Yes, correct. 5.25 bar. Others has also got it. Great, Sanjana. Anyone else has also got the 5.25 bar? Santosh, Swara, Shashank. Yeah, you got the answer? Shanmugam, are you able to get the answer? 5.25 bar. Take about a minute. I'll give some time for others also. I hope everyone is trying the. Okay, that's more important. If anyone of you get the answer, please tell me. Okay, pretty simple question. Yes, I hope I'm visible now.
Yes, sir, I get 5.25 bar.
You are also getting? Okay, great. Great, Santosh.
Thank you.
Solution. So we are given the spark ignition SI engine. Basically, an Otto cycle is given. We have already discussed it in very detail. The compression ratio, that is R, is given to you 5.5. Okay. And work output is given. So net work done is given in terms of a clearance volume eventually. So we have to identify the mean effective pressure. So what is mean effective pressure? Just we saw the expression mean effective pressure into swept volume is your work done. Okay. So we don't have swept volume so far, but we have a work done. So what is work done? 23.625 into 10 to the power of 5 into swept clearance volume. And here PM into swept volume. Do we know any relation between swept volume and clearance volume? Yes, we know it's a clearance ratio. It's a clearance ratio. But do we have a clearance ratio? No, we don't have a clearance ratio. We have a compression ratio. But can we get clearance ratio from a compression ratio? Yes, we can get that. We have already seen this relation, that is R is equal to 1 plus 1 by C. So we are given R as 5.5, 1 plus 1 by C. So from here, 4.5 is equal to 1 by C. So what will be C? C will be how much? Let us say C is equal to 1 by 4.5. Okay. Now we have C as well. So if we come back to this equation, so PM is equal to 23.625 into 10 to the power of 5 into Vc by V swept. And this is nothing but your C. That is your C. And C you can put it from here. So let us put, so 23.625 into 10 to the power of 5 into 1 by 4.5. And we want to give the answer in bar if, so let's keep 10 to the power 5 as it is. So if you divide 23.625 by 4.5, it will be 5.25 bars. That is your mean effective pressure. Okay. So this how we will approach this question. I hope this is pretty much easy question. Everything was given to us. How we need to approach. Clear? Any doubts? Please ask. Those who were not able to get, are there any doubts here? No doubts? Great. So I'll give another question, and it's a very good question.
Sir, sir,
Yes.
can you
Yes.
please scroll back, sir? Can you please scroll
Yes.
back? R equal to 1 plus 1 by C. What is mean by R? Can you please explain, sir, that step?
R is a compression ratio given in the question, 5.5. We have already seen this terminologies in our previous tutorial. R is stands for compression ratio, which is clearance ratio of clearance volume to swept volume. Oh, sorry. R is basically higher to lower. So compression ratio is given, and clearance ratio is clearance volume to swept volume. So C we got
1
from
by
there.
C. 1 by C is an compression ratio. Stands for compression ratio. 1 by C. Or 1
No,
plus 1
no.
by C.
C is your clearance ratio,
Okay.
and R is your compression ratio.
Okay. 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 Okay.
Okay. Any other doubts?
Yeah.
Okay.
Okay. Okay.
Next question. Pressure at no doubt. Please, can you keep yourself on mute? 25% of stroke. Okay.
Sir, you are not audible. You had muted yourself.
Am I audible now? Hello?
Yes, sir.
Okay, okay, thank you. Yeah, I was saying pressure at 25% of stroke is 1.5 bar, and 75% of stroke is 4.5 bar. And it follows the law. PV to the power of 1.3 is equal to constant. Okay. Find air standard efficiency. And where the adiabatic index is given as is equal to 1.4. Okay. So note that nothing is given that find the air, calculate of auto efficiency. We have not mentioned this thing here. You have to just find the air standard efficiency. Okay. Do it. Take few minutes and do it. It's a good question you have. Students might make mistakes. If anyone of you get the answer, please let me know. Anyone is able to get the answer? What is the value of efficiency? Make sure that the process is not isentropic this time. So that's why the adiabatic index as well as have, and the other index, polytropic index, is also given. And it is not mentioned that we have to find for Otto cycle. It just said that find the air standard efficiency. For which cycle? The cycle has been described. That 25% of stroke and 75% of stroke. Anyone is able to do?
Sir, is it 57.8%?
57. No, it is 58.28%. You can just recheck your calculations.
Approximately it will be same, sir. 57.88% I have got. Maybe I had missed
What
some
what is
digit
the
or value.
index you have taken? Polytropic index value you have taken
Uh,
while calculating?
7.9.
No, I'm asking in the air standard efficiency formula, what is the adiabatic index or polytropic index? What value you have taken?
For polytropic, I has taken 1.3, and for adiabatic, I has taken 1.4.
So answer will come through which value? 1.3 or 1.4?
So for calculating Vs by Vc, I had taken polytropic index, and for finding the efficiency, I has taken adiabatic index.
Okay. Put the 1.3 only in your answer and then solve what is the value you are getting.
Okay. Wait.
What about others? Anyone else has also got?
So the value is coming 48.09%.
Okay. All right. Let us solve that. I think there is doubt for others as well, but it's a good question. Let's try this. No, I think I'm visible. Yeah. Okay. So it's given that pressure for a cycle, one of the cycle, it is not told that it's a diesel cycle or an auto cycle. Okay. Pressure at 25% of the stroke is 1.5 bar and 75% of the stroke is 4.5 bar. So eventually it is, if you go through a compression scenario, because pressure is increasing from 1.5 to 4.5. So that means it's a compression process is happening. First thing is that. Then it is said that it is not following isentropic compression. It is following some law PV ratio r 1.3 is equal to constant. Isentropic will come when it will be adiabatic reversible. So examiner has given you adiabatic index equal to 1.4 just to confuse the student. It won't be used anywhere because they have said that our cycle works on a compression process which is not isentropic, it's polytropic. That is, index is 1.3 instead of 1.4. It is not adiabatic index. And we need to find the air standard efficiency. From this only we get to know that it's not going to be an Otto cycle, because in Otto cycle it is an isentropic compression. But for other cycle it is not isentropic compression, it's a polytropic compression. Okay. So let us solve solution. So it's going to be a, let us make an axis. The compression process eventually P and V. So let's make a compression process from point 1 to point 2. It's a compression process. It is said that at 25% of the stroke. What do we mean by 25%? So strokes start from 1 to 2 during the compression. Strokes start from 1 to 2. So 20, from position 1 to 25%, let us say 25% happens till here. Okay. Denote is a position as A. And pressure is given to us at A is 1.5 bar. Okay. Then it is said that at 75% of the stroke, pressure is 4.5 bar. So 75% of the stroke means from 1 when the compression is starting. So 75% of the stroke has happened. So that means our pressure will be, let us say it is 75%. And this was the position 2. So from here till here, it is 75% has happened. Okay. And pressure is given to you as how much? 4 point. Let us say this is position B and pressure is given as 4.5 bar. So this is a pictorial representation what is happening. Pressure at A and pressure at B. So we know that air standard efficiency is 1 minus the relation we got, that is gamma minus 1 if gamma is adiabatic index. But here the process is not adiabatic. It is polytropic because gamma is different something. That is 1.3 for this. We don't know what is the value of the R. We need to get the value of R. Okay. So how we will get that? First, we know that from the relation PV raised to power 1.3 is equal to constant. It's given to us. So if we apply this relation between point A and point B, because this is following the same compression, same path. So pressure at A, volume at A to the power of 1.3 is equal to pressure at B, volume at B to the power of 1.3. Okay. So what is pressure at A? It is 1.5 bar. Pressure at A is 1.5. And volume at A, let us suppose it is VA to the power of 1.3 only. Pressure at B is 4.5 bars and volume at B is 1. VB to the power of 1.3. Okay. Now, what will be volume at A in terms of swept volume and clearance volume? So we know that. Let me use some another color. Yeah. So this whole from point 1 to point 2 is nothing but your swept volume, right? This is your swept volume, and this is the remaining is your clearance volume. Okay. This is your clearance volume. If I am saying 25% of the stroke has happened from 1 to A. From 1 to A, 25% of the stroke has happened. So how much volume is remaining now? That is 75% of the stroke is yet to be completed, right? So volume at A will be 75% of the swept plus the remaining clearance volume, plus the remaining clearance volume. Again, I am explaining, carefully listen, that if I am saying by 25% of the stroke has happened, that means from position A to position 2, 75% of the stroke is still remaining. 1 minus 100 minus 25 is 75%. So that means 75% of swept volume is remaining, plus some clearance volume will also be there in the cylinder. So what will be volume at A then? Eventually, volume at A will be this volume at A will be V clearance plus 0.75 times of V swept to the power of 1.3 to the power of 1.3. Similarly, if I am saying volume at what will be volume at B? Volume at B. Let me write these points here. So this is volume at A and this is volume at B. So B process has completed 75% of the stroke. So from 100, 75 is completed. The remaining is 25%. So remaining volume is this much, 25 plus the swept volume. 25 plus swept volume. So volume at B will be how much? V clearance, sorry, V clearance plus 0.25 of V swept to the power of 1.3. Okay. Now let us divide the ratio. So we will be having Vc plus 0.7 time of V swept to the power of 1.3, Vc plus 0.25 to the power of Vs to the power of 1.3. I have taken this side and this 1.5 on the right hand side. I am doing this is equal to 4.5 by 1.5. Okay. Let us take out Vs common. So this will be Vs to the power of 1.3. Sorry. So it will be Vc by Vs plus 0.75 from denominator also Vc by Vs plus 0.25 And 4.5 by 1.5 is 3 eventually. Okay. So this and this cancels out from numerator and denominator. VC by VS, we already know that clearance ratio is VC by VS. So C plus 0.75 to the power of 1.3 by C plus 0.25 to the power of 1.3 is equal to 3. So when you solve this, you will get your C value as how much? Or what we can do, we can write this in different way, to the whole power 1.3. Okay, this remains the same. And if you take 1.3 on the right hand side, you will get the C value eventually. So C plus 0.75 by C plus 0.25 is equal to 3 to the power of 1 by 1.3. From here, if you solve it, your C will come out to be 0.128. C will be 0.128. And we know the relation between R and C now. Since compression ratio is equal to 1 plus 1 by clearance ratio. Put this value of C here. So it will be 1 plus 1 by 0.128. So compression ratio will come out to be 8.9. Your compression ratio is now 8.9. Now you put this value in the air standard efficiency. Air standard efficiency is 1 minus 1 by R to the power of gamma minus 1. Here gamma is equal to 1.3 for our current process. It is not auto cycle. So 8.9 to the power of 1.3 minus 1. So the final answer will come out to be 58.28%. Any doubts? Please ask. It was a very good question, actually. Any doubts?
Sir, actually, from this, the value is 48.09, and if we use adiabatic value 1.4, then the value will come 58.28. Actually, prior I has done a mistake,
Okay.
so my value was not matching.
Now is it matching?
Yes, sir. I has used 1.4 only. It is matching 58.28.
With 1.4, right?
Yes,
Then it will be 58.28.
yes, sir.
Okay. All right. Any doubts to anyone else? So why 1.4 will come here and not 1.3? The question arises this. The gamma value will be 1.4, not 1.3. The reason behind this is it has been asked that it is an air standard efficiency. So air standard efficiency is with the polytropic index to be adiabatic. That is your isentropic process. Okay. Then only the air standard efficiency will be calculated. But your process in the cycle is not isentropic. That's why the C value, that is your clearance ratio, and from there compression ratio is calculated based on the polytropic index 1.3. Okay. Let's do another question. Any doubts to anyone else? Okay. In air standard diesel cycle, has a compression ratio 17 and cutoff takes place at 10% of stroke. Assuming gamma of air is 1.4, determine air standard efficiency. Okay, air standard efficiency. Please solve it. So anyone got the answer? Just you have all the values just put in the relation of the air standard efficiency of diesel cycle. We have derived this in our previous tutorial. Did anyone of you got?
Or is it 59.06%?
Yeah, correct. 59.6%. What about others? Ratish, Shivlingesh, Santosh. Okay, let us solve this then. So let us come to the solution of this. So we know the formula directly. We have derived this. Air standard efficiency of a diesel cycle is 1 minus 1 by R to the power of gamma minus 1. Then rho to the power of gamma minus 1 by gamma times rho minus 1. This was your relation. Okay. In the question, it is given compression ratio is 17. So R is given to be 17. You don't know what is rho so far, but I have explained this point that cutoff take place at 10% of the stroke. When it is said like that, the cutoff. So if you go to the cycle once again, so pressure volume plot, if I make 1, 2, 3, 4. So this is your process: isentropic compression, heat addition at constant pressure, isentropic expansion, and heat addition at constant volume. So cutoff take place at 10% of the stroke. So that means V3 minus V2, that is your cutoff. From cutoff point is 3. and starting was fuel injecting starting was at 2. So V3 minus V2 is 10% of, that is 0.1 times of your stroke. Stroke happens from 1 to 2, V1 minus V2. Okay. If I, we have already seen this, if I divide by V2 both sides. So V3 by V2 is your cutoff ratio. Rho minus 1 is equal to 0.1 times of V1 by V2 is your compression ratio. Okay. So rho minus 1 is equal to 0.1 times compression ratio is given as 17 minus 1. So your rho will come out to be 2.6 from here, 2.6. Okay. Put this value. Now you have R, you have rho. Put this value in the efficiency formula. 1 minus 1 by 17 to the power of gamma minus 1, 1.4 minus 1, rho to the power of gamma, rho to the power of gamma minus 1 by gamma times rho minus 1. Put this value, you will get your efficiency as 59.6%. Okay. Any doubts in this? Or all clear? Yes or no? Is it clear or any doubts? Please be active. Santosh, is it clear?
Yes, sir. I get
Okay.
the answer, sir. 59.6.
Okay. Okay. Now let's come to the concept of burning of the fuel, how the fuel is getting burned. Okay. So there is
Sir,
a fire.
sir, hello.
Yeah. Yes.
How to solve in virtual calculator? Can I give you the hint or something?
What do you mean by
This step
virtual?
particularly, yeah, NPTL thesis and virtual calculator. How to solve? Can I give the tip or
What,
give
what do you want to solve in the virtual calculator? That is my question.
eta equal to 1 minus 1 by divided by 17 whole to the power of 1.4 minus this
So
last formula.
again, you can't solve the whole complete expression in the single way. You have to first solve this part, then solve this part, write
Okay,
it, then this part,
okay,
then multiply and divide.
okay,
This way only you can, yeah. Okay.
okay. Thank you.
So I was talking about a concept of fire point temperature and self ignition temperature. So what do you mean by fire point temperature? It's basically when you forcefully ignite the fuel. That is your fire point temperature. But self ignition temperature is that when you don't forcefully ignite the fuel. Okay. But in mathematical terms, both are same. Okay. So let us come to the power stroke scenario. Power stroke scenario where, let me make the cylinder once again. So this is your piston at TDC, and this is your BDC. Okay. So work, and this is your spark plug. Let us see. Okay. So both the valves are closed at this point of time when the power stroke is happening. Okay. Both the valves are closed. So when the fuel is ignited at this point of time, very sudden high pressure happens and the displacement of the piston happens. So you get a work done, that is P delta V. So when the displacement happens, so work done is P delta V. That is your work done. And very sudden high pressure is achieved. Okay. Sudden high pressure is achieved. Let us make it using. This is a scenario. Okay. But what happens from suction to compression scenario? When I'm saying that how the fuel is burning in this scenario. So again, I make this. Okay. This is again your, and here also. This is your BDC. And this is your TDC. So when volume was sucked inside this, let us first remove this. When there are suction stroke is happening, the air fuel mixture is getting sucked inside the cylinder. So the particles are basically very far away spaced. Okay, very far away spaced. Okay, you can say. But as soon as the cylinder reaches to the TDC position during the compression stroke, to the TDC position, what happens? The particles are now not far away space. They will be very near to each other because they have been compressed. Okay, they have been compressed. Let us not use this color first. They have been compressed. And as soon as you provide the spark, then the particles start to burn. Okay, this happens after the compression. Now what happens in this scenario? Suppose at this situation you had a fuel particle during the suction. Suppose this is your fuel particle. Let us zoom it out. Okay, let us zoom. So this is your fuel. Okay, and fuel is nothing but your hydrocarbon. Fuel is nothing but your hydrocarbon, and it is a air fuel mixture. So eventually air is also there. It's a mixture of a fuel and air. Okay, fuel and air. So fuel is surrounded with air. Fuel is surrounded with air. Okay. Now let us zoom this fuel to here. Okay. It's a mixture of hydrocarbon. So hydrogen being lighter is outside and carbon being heavier is inside of the fuel. Okay. So in the hydrocarbon structure, your this will be your carbon, whereas this will be your hydrogen. Okay, this will be your hydrogen. So okay, so carbon is covering the core, whereas outer part is the hydrogen. So carbon is covering the core, and this is outer region. This is your outer hydrocarbon region. So every fuel has its calorific value. So what happens when we provide the spark? So first of all, the hydrogen, that is your outer layer, gets burned. So hydrogen burns first, and it burns very rapidly, because the calorific value of a hydrogen is very high compared to the carbon. And then what happens? The carbon burns. Okay. So when the compression happens, basically, let me make it here. So this is your air fuel mixture. So when the compression happens, okay, and you provide the spark, let us say spark. So the fuel inside it gets burnt with the process that first hydrogen burns and then the carbon burns. And the temperature is reached at T flash, that is flash point temperature. T flash. Let me write T flash. And you're just providing the spark. Fuel was there, which was very much compressed at a very high state. You just provide the spark. The temperature inside the cylinder at before spark, just before spark, is T flash. As soon as the sparking has been done, so because of compression, the temperature has reached T flash. As soon as the sparking has been done, the temperature will reach the fire point. The temperature will reach the fire point. Let me draw here. After sparking, the gas will expansion of the gas. And here the temperature has reached T fire after the sparking. So this how the process takes place. Okay, that fuel is nothing but your hydrocarbon. As soon as you compress, initially it was a air fuel mixture during the suction. As soon as you compress, the temperature inside the cylinder is a flash temperature. Immediately you provide the spark, the fuel burns. How? First the outer layer burns, then the core burns, and the gas expand. So from T flash to T fire temperature reached. That is a fire point temperature. You forcefully ignited the fuel. Okay. So let me write it here. H burns first. Hydrogen H burns first, and rapidly. Why? Del of hydrogen, that is calorific value, is more than that of a carbon. How in terms of a chemical formula it looks like? So so our fuel is hydrocarbon. So it will be C3H8 is your fuel. It is mixed with oxygen and nitrogen, that is your air, 5 times O2 plus 79 by 21 of N2 is nothing but your 4H2O plus 3CO2 plus 79 by 21 of N2. Okay. So this was initially your air. This was initially your fuel. This was your air. And this is expanded or exhaust gas. Expanded or exhaust gas. Okay. Which comprises of delta of H, that is hydrogen, and delta of carbon, and these are nothing but your calorific values. So fuel carry hydrogen and carbon, and eventually it has a calorific value, and hydrogen is a higher calorific value compared to a carbon. That's why it burns first. Okay. What is a stoichiometric or perfect combustion? Or we say that what are other types of combustion? So this is nothing but your stoichiometric or a perfect combustion happen. That whatever amount of fuel you wanted with the amount of air, that is a balanced approach, and you get the complete usage of the fuel. That is your stoichiometric or perfect combustion happens. Stoichiometric or that means when you are pedaling your car or accelerating your two-wheeler, you are gradually doing that, not suddenly. Then only a proper stoichiometric combustion will happen. That is, right amount of fuel and right amount of air will get mixed, sucked into the cylinder during the suction stroke. But if you suddenly give a jerk or suddenly press the pedal of the accelerator in the car, then it's possible that fuel will be less or air will be more, or fuel will be more, air will be less. Okay, and that gives us different kinds of combustion, that is lean, rich, or super rich combustions happen. Okay, so other types of combustions are basically lean. What do we mean by lean? When air is more, okay, compared to fuel is more. What is second? Rich. Rich combustion, that is when the fuel is just more, just slightly more compared to the air. When fuel is and third is super rich. when fuel is very high compared to the air. When fuel is more. Okay, that is wastage of fuel. Combustion will not happen properly and unburnt hydrocarbon will come out of the exhaust. Okay, so these are different kind of combustions. Okay, now we have seen the suction stroke, we have seen the combustion stroke, that is your power stroke as well. Suction, compression, and power stroke. Now coming to the how the actual expansion is happening. Okay, exhaust is not expansion, sorry, actual exhaust is happening in the process. Okay, let us see. Just give me a minute, please. I'll be back. Okay, I'm back. Yeah. So I was telling about the exhaust. So let me make the cylinder once again. I hope I'm audible. So during the exhaust stroke, our piston is just at the bottom dead center. The exit valve is open at this point, and almost 90% of the gas is exhausted out. Okay, now the exhaust will happen. So exhaust. Okay, so here what is happening? Still the pressure in the exhaust is greater than pressure than atmosphere. Then only because of the pressure difference, the exhaust gas can go out from inside cylinder to the outside. Okay. So if pressure is high, so these exhaust gas has temperature also high compared to temperature of atmosphere eventually. Okay, much high you can say. Okay. So what happens now when we are doing the exhaust stroke from BDC to TDC when we are going? Then remaining 10% of the gas is taken out. So 90% of the gas is almost coming out, but the remaining 10% of gas during the exhaust stroke goes out, and pressure inside the cylinder is almost equal to the pressure of the atmosphere. That's why because of the inertia, the piston moves up. So almost initially the temperature during the start of the before just start of the exhaust stroke, the pressure was higher. That is why 90% of the gas is exhausted out. But as soon as the exhaust stroke starts, the pressure is almost equibalanced from the atmosphere. Okay, so let me write like this. As soon as now the stroke starts, okay, the valve is still open. The remaining 10% will go out during the exhaust stroke. Exhaust. Let's write like this. Remaining 10%. Exhaust. And the pressure inside Pressure of exhaust is almost equal to pressure of atmosphere at this point of time. Okay. So after the heat rejection, the piston move from bottom dead center to the top dead center to throw out the remaining gases out of the cylinder. Let me write this. After heat rejection at constant volume, the piston let me write the PDC here. The piston displaces. Oops. From BDC to TDC to throw out remaining exhaust gases out of cylinder. Now there is a catch, very important catch. Now when the piston is moving from BDC to TDC, why I have written BDC again, it should be TDC. Now when the piston is moving from BDC to TDC, what happens at very near to the exhaust valve? At very near to the exhaust valve get closed. It's not that we will close the exhaust valve when it has exactly reached the BDC, TDC, top dead center. Okay. So at very near to the exhaust valve, top dead center, we will close the exhaust valve. We will close the exhaust valve. But there is a reason why. Why do we do this? It is because time for closing of the exhaust valve is more, because of which the temperature and the pressure is higher inside the cylinder. Okay. So basically these valves operate on a camshaft spring mechanism, with a spring loaded mechanism on the valves. Okay. Through a timing chain. Okay. So from the crankshaft, the chain is connected to the valves, and those are connected to some gears, because of which the wheels and a camshaft assembly, because of which the spring is pushed down during the exhaust, and for most of the time it is closed. That is why time of closing of the exhaust valve is more compared to the opening. Okay. So what happens? Let me make one by one, step by step. So this was figure number, let's give numbering. This was figure number 1 when the power stroke has happened. This is figure number 2 when the exhaust is going to start, and figure number 3 how the exhaust is going to start. So let us draw. Okay. So let us say this is our TDC, and this is a position where piston is. Okay. Connecting rod, crank rod, and crankshaft. These are moving circular motion. So what is happening? Let us say this is a position A. This position is said to be A, and it is going from A to TDC, A to TDC. Okay. So at this position A itself, at the position A itself, the exhaust valve will open. This volume is still to be reached, but the exhaust valve will close at this point. It's not that when it will reach completely to the TDC, we will close the exhaust valve. The reason behind this is it is basically a camshaft assembly. Okay. So if I say this is a Let me make. If you see the timing chain, this is your camshaft. It is moving like this. I'm making a very elongated zoom figure. Okay. So it is a camshaft. It is moving like this and it is connected to a spring loaded valve. That is your inlet and exhaust valves. Okay. And this valve is having a spring mechanism. Okay. This is your valve. And this is your spring. So this is moving actually. We have this exhaust valve and this is moving. So when it is pushing down, then the valve is getting opened inside the cylinder. But it is for a short duration of time. So time for opening is less, then again the spring will pull it back. The spring will pull it back and again it will be closed. The valve will be closed. So time for closing will be till from here to this point, until unless this tip of the shaft, this tip, sorry, this tip is in match with this tip or some region of the tip. Okay, it's just in touch with the spring valves. Okay, then only the valve will be opened. For remaining time, it will be closed. So that's why time for closing of the valve is more compared to time of opening. Okay, so when the piston has moved from BDC to A position, from BDC to position A, the exhaust valve is closed at that point of time itself. And because of which the temperature and the pressure is high. And from here only the concept of volumetric efficiency has come. Okay. So what happens if I open, basically if instead of here, I say that my exhaust valve will close here only. Okay. And then only my inlet valve will open. Okay. So if inlet valve opens when the exhaust valve, this piston reaches exactly to the TDC, then what will happen? The fresh air fuel mixture is also entering, and as well as the valve was initially open. You are saying that it will close when it will reach here. So exhaust is also happening at the same time. So because of which suction is yet to happen when it will reach to the TDC. Suction is still yet to happen from TDC to BDC in the next process. But because of opening of the inlet valve and opening of the exhaust valve at same position, the because we say na that inlet valve will open when it has reached to the TDC. But we are also keeping it open just before reaching the TDC till here. So what happens? Opening and both of the walls are open and both of the air fuel mixture, the exhaust is taking out the gas and some of the air fuel mixture will also go with this, which is unburnt, non using like not at all utilizing your resource. That is your fuel, which is limited in nature. First thing is that you don't want this. You want the valve to be exhaust valve to be closed just before reaching the TDC. Okay, this is not the very high volume. This is very small volume. Okay, and it is connected to, like it is connected through this camshaft spring loaded assembly, and it is maintained through this. First reason is this. Okay, let me first remove this. I'll write all these points. Don't worry. Okay, yeah. Next, the air fuel mixture will reach. Why? Why the now the question might arise that pressure of the exhaust and temperature is very high. Then the temperature is very high. It is carrying out the gas. But the air fuel mixture which is entering has a higher density, and we know that P is equal to rho RT. If density is high, that means pressure of the inlet of the air fuel mixture will also be high. So air fuel mixture is also entering at that point of time and it is taking out the coming out with the exhaust. Fresh air fuel mixture is coming out, which is the unburned hydrocarbon is there and it is a source of pollution. That is why we are closing the exhaust valve just reaching before the top dead center. Okay. That is why, and then we start the suction of the after it has reached the TDC. Till then also exhaust valve will not inlet valve will not open. We will because the pressure inside the cylinder is still higher. The pressure inside the cylinder is still higher. So when it has moved from A to TDC and then from TDC to some position B, then only the suction will start, because the pressure here need to be higher compared to the cylinder. Then only suction can start. If the pressure difference is not there, the pressure is not higher in the inlet of the air fuel mixture, until then it will not suck the air fuel mixture, because of which the complete suction won't happen and the concept of volumetric efficiency comes here. That is actual volume. Actual volume, the swept volume is from position B to position DDC, but in theoretically it should happen from the TDC to VDC. That is why a volumetric efficiency concept came. Okay. So volumetric efficiency plays a very important role now here. Volumetric efficiency plays a very important role. Yes, I think. Right. Volumetric efficiency plays a very important role for the power generation, because you want stoichiometric amount of the fuel to be coming out, perfect stoichiometric combination all the time. But in the real world, it cannot happen all the time. But you want the required actual amount of the fuel should get sucked in, air fuel mixture should get sucked inside the cylinder, so that adequate amount of power can be generated from the engine. That is why, if you have heard an IV Tech technology by Honda, I think it came back in 2000, initial year 2001. If you see in the cars of back side of the car of Honda cars, you will see IV Tech. So it's basically intelligent valve timing variable, intelligent valve, something like opening of the intelligently through electronic circuit. They are opening this camshaft spring loaded assembly, not manually from the from the timing chain. Okay, that is why they patented this thing and they are using on their cars, IV Tech technology. Okay, so that is why, and they were able to achieve the volumetric efficiency from 80 to 90%. Okay, whereas other manufacturers at that time were having a volumetric, they were not able to get the complete air fuel sucked in inside the cylinder at that, like less than 80% at that point of the time. Okay, so I'll write all these points. This was the figure number 3. Let's make the figure number 4 also. So when I'm saying this is my TDC, this is my TDC position. Now my piston has moved from this to, suppose, some position this downward. Okay, this is a position B. Okay, this is a position B from TDC to onward during the expansion, during the actual suction, sorry. So suction is happening, actual suction is happening from this position to this position. Actual suction, but theoretical suction was happening from TDC to, this is PDC, let us say. Theoretically suction was happening from TDC to BDC. V theoretical. But the operation of the inlet exhaust valve mechanism is happening here, where the less than the theoretical suction. Okay, V actual suction. V actual suction. So from this point, then only we can say that cylinder pressure is at point B only. So at this point at TDC, P in the cylinder, sorry, not this. Now at this point only P in the cylinder was equal to P of atmosphere, from where, and then only a higher injected fuel can come inside it. Okay, and at this point P of cylinder is greater than P of atmosphere. Now from start of the B, the fuel will start injecting inside. Okay, air fuel mixture will start injecting it. So let me write this heading as end of exhaust and beginning of suction. So at very near to end of exhaust in figure 3, point A, that is in the figure number 3, the point A is there. Okay, this point A. At just very near to the exhaust valve is closed and piston movement from A to TDC compress the exhaust gas remaining inside cylinder. Okay, and as pressure inside the cylinder is high, is not high, slightly more, than atmosphere. So that is P of cylinder is almost 1.05 to 1.11 times of P atmosphere. Okay, it's just slightly higher. Okay, so pressure becomes slightly higher. So hence at the beginning of the suction stroke, suction stroke, that is figure number 4. Okay, the last figure which we made, this figure. Okay, inlet valve is open. Very important concept. I know it might have been difficult to absorb, but again, that is why I'm writing the points so that you again are able to understand. And if you are still in confusion, you can again watch the recording and listen what I have said. Okay. Figure 4, the inlet valve is open, but still no entry of fresh air fuel mixture, AFM, air fuel mixture. Then after that, after some moment getting wasted, getting wasted during suction stroke, that is from TDC to point B, from TDC, this point, from TDC to point B, some movement has been wasted. That is TDC to B, TDC to B. The pressure inside cylinder is almost pressure of atmosphere. Now the pressure has reduced. Then after that, the actual suction will start. Then actual suction of fresh air fuel will begin, which is less than the theoretical. less than theoretical. That is V actual is less than V theoretical. And from here only the concept of volumetric efficiency came, which is volumetric efficiency, that is efficiency with subscript of V. It is basically a ratio of actual suction volume of air that actually entered into cylinder entered into cylinder to the theoretical suction of swept volume. That is efficiency, volumetric efficiency is V actual by V swept. Okay. It is also called as second law efficiency. Okay. Volumetric efficiency or second law efficiency. Second law efficiency. And how you will get the actual volume? So actual volume will come from the gas relation, that is PV is equal to MRT. Okay. So actual volume is calculated. Pressure into volume is equal to mass at that for the actual R and at temperature T1, where P1 and T1 are basically your atmospheric conditions. Okay, where P1 and T1 are atmospheric conditions. Okay, and swept volume, you get from pi by 4 d square L. We have already seen that. Okay, we have already seen that thing. Any doubts in understanding this concept? Because I'm going to give a question on this. Please ask me right now if you have any doubts. Otherwise, we'll start with the question. It will be a very good question. Okay, no doubts. Now let's come to the question then. Cylinder ratio is 1.5. Engine is based on diesel cycle. Clearance ratio is 10%. Work done is 1500 joule. Cutoff take place at 10% of stroke. Section pressure is 1 bar. You have to determine first efficiency of cycle. Second, mean effective pressure. Third, cylinder dimensions. Okay, please do it. Take 5 minutes and do it. Everything is given in the question. You just have to put the values and get the answers. You need to have the relations of work done from thermodynamics for the processes. You need to remember that. It will be required. I expect that everyone is done with the thermodynamics. And if you have not done or you have any doubts, already I've taught thermodynamics, and its videos are also available on my same YouTube channel, NPTL with Varnit, in the playlist with the named as thermodynamics. That also I taught on NPTL only. Even I would appreciate if you guys uh, like share all these things with your uh, colleagues or batchmates so that they can also join the session, motivate them to join, or they can at least watch the recordings or the notes. That will be helpful for them as well.
Sir, sir,
Yes, yes, Santosh.
you will record and upload on your website and YouTube, sir. NPTL with Varnit.
Not website, it's on the YouTube.
Sorry. No, sir. Tomorrow, last week, Wednesday, I received mail from NPTL team from Google Docs
Mm-hmm.
document.
Yes,
So that's why I'm asking, sir.
yes. NPTL team also mail
Okay.
you all, but you can also, I'm just
You
saying
are
that you can, uh, those who want your friends or your colleagues, your batchmates, you can also share among them as well so that they can also learn and get benefited from this.
okay, sir. Okay, thank you.
Yeah. Anyone has done the question? Efficiency of cycle, anyone has got? Okay, let's solve it then. I know it's a pretty tricky question. Let's solve. Okay, let's come to the solution. So again, it's a cylinder ratio, that is L by D ratio or over square ratio, that we have already seen. It's given to be 1.5. Engine is a diesel engine cycle. Clearance ratio is given as 10%. That is, your C is given 0.1. Work done is given, net work done is 1500 joule of the cycle, we know. Cutoff take place at 10% of stroke. Just now we saw that rho minus 1 is 0.1 times of R minus 1, the relation. Suction pressure is 1 bar. Okay, pressure is known, and you need to find the determinant efficiency of the cycle. So first of all, efficiency, this question just now we have done. So efficiency of diesel cycle is 1 minus 1 by R to the power of gamma minus 1 rho to the power of gamma minus 1 gamma times rho minus 1. But we don't have R, or do we have? Let us see. So we know that C is 0.1. So, and R is equal to 1 plus 1 by C. So 1 plus 1 by 0.1. So this gives you R as 11. R as 11. Now we don't know rho. How you will get? Rho minus 1 is 10%. How much? Cutoff take less 10% of the stroke. So 0.1 times of R minus 1. Just now we saw this relation. So is equal to 0.1 into 11 minus 1 is equal to rho minus 1. So from here, rho will come out to be 2. Now you have rho, you have R. Put this value in the efficiency formula, you will get the efficiency. Efficiency is 1 minus 1 by R to the power of gamma minus 1, gamma is 1.4, into rho to the power of gamma minus 1, gamma times rho minus 1. So from here, the efficiency will come out to be 55.13%. 55.13%. This is your answer for the first part. Now let's come to the second part. Mean effective pressure has been asked. So what is mean effective pressure? PM into swept volume is net work done. You have the work done 1500 joules. Okay, 1500 joules. Mean effective pressure we don't know. We don't know the swept volume so far. Okay, let's get that. So in the 1 to 2 compression process, so net efficiency you got, first of all, efficiency is nothing but net work done upon heat added at constant pressure for the diesel cycle. And this is given to be 0.5513. We just got it from here. Okay. Net work done is given as 1500. Heat addition at constant pressure you can get from here 0.5513. So heat addition at constant pressure will be how much? It will be 2720.54. 2720.54 joules. This will be a heat addition at the constant pressure. Okay. Now we know that net work done can also be written as work from compression 1 to 2. Let me make the cycle once again so that you guys are again aware. So this is your PV cycle. One, two, three, four. Don't forget to make the arrows. 1 to 2 is compression, 2 to 3 is heat addition at constant pressure, 3 to 4 is expansion, isentropic, and 4 to 1 is heat rejection at constant volume. 1 to 2 plus, again 2 to 3 also will be work done this time because it's not at constant volume. Work done is P into dV. So volume has changed from 2 to 3. So work done 2 to 3 plus work done 3 to 4. 4 to 1 will be 0 because change in volume is 0. P dV, dV will be 0. Okay, so this is your work done. So 1 to 2 is the isentropic process. What is the formula for the isentropic work done in thermodynamics? It is P1 V1 minus P2 V2 upon gamma minus 1. So work done 1 to 2 is P1 V1 minus P2 V2 to the power of on the base of gamma minus 1. What is work done 3 to 4? Again, it's an isentropic process. Work done 3 to 4 will be higher pressure P3 V3 minus lower pressure P4 V4 by gamma minus 1. What is the work done for 2 to 3? So work done from 2 to 3, pressure is constant, that is P2 into V3 minus V2, PdV for a closed system. Okay, PdV. Now you don't know the values of these. Okay, do you know? No, so far you don't know all the values. You just know P1. Okay, We also know from the relation, since P2 by P1 to the power of, for an isentropic process, P2 by P1 to the power of gamma minus 1 by gamma is equal to V1 by V2 to the power of gamma minus 1. Okay. What is V1 by V2? It is compression ratio. So P2, what is P1? P1 is given to be 1 bar. Gamma minus 1 by gamma, that is 1.4 minus 1 by 1.4. V1 by V2 is your compression ratio. This is your compression ratio. Compression ratio we have already calculated above. It is 11 to the power of 1.4 minus 1. So from here you will get the pressure at position 2, which is equal to pressure at position 3 as well. Constant pressure 28.704 bar. So pressure you got to know at 1, 2, 3. Okay. So you can put the values. Can you? 1 you know, 2 you know, 3 you know, 4 you don't know so far. We need to get the fourth pressure also. Let us get one by one. So yes, so V1 by V2 we know that is how much. What was the question? Question was to get the swept volume eventually. Swept volume. So swept volume, since R is equal to 11, that is nothing but your V1 by V2 is equal to 11. Okay. And V2 is your clearance volume. And V4 and V1 are equal. If you see from the graph, V4 and V1 are equal from the cycle. Since V1 is equal to V4 and V2 is your clearance volume Vc. So it can be written as V4 by Vc is equal to 11. Okay. Also, since we know that cutoff ratio is nothing but V3 by V2. So cutoff ratio we also have got V3 by Vc, since Vc is V2. So V3 is equal to 2 times of Vc, 2 times of Vc. Now we have V4 in terms of Vc, we have V3 in terms of Vc, okay, and we have V2 in terms of Vc, and V1 and V4 are same. So we can also put these values V3, V1, V2, V4 in all the work done process, right? We are having the values. But question is how you get the Vc, first of all, how you get the Vc. So since we know that PV is equal to MRT, multiply and divide by multiply gamma by gamma minus 1 both the sides. Gamma by gamma minus 1 PV is equal to M gamma by gamma minus 1 times R and T. Do you remember that this relation is of CP? CP is also in terms of gamma R written as gamma R by gamma minus 1. So this is your CP. So what can we say? Gamma upon gamma minus 1 PV can also be written as MCPT. And this is nothing but your heat addition at constant pressure. Heat addition at constant pressure. So this is a very important relation. We have derived that heat addition at constant pressure can be written as, for a diesel cycle, P2, not for a diesel cycle, for any process, P2 times V3 minus V2 into gamma by gamma minus 1 for now. Okay. When V2, V3 will be equal, it will be 0 heat for our Otto cycle, but if not, so V3 is 2 times of Vc. We have seen this. V3 is 2 times of Vc and V2 itself is Vc. We will put this, and we know the heat addition. We have already calculated heat addition at constant pressure here. If you see heat addition at constant pressure, we have already calculated. Heat addition at constant pressure is 2720.54. P2 we have already got. What was P2? This was P2, 28.704. 28.704 into 10 to the power of 5, because it was in bar. 2 Vc minus Vc, 1.4 by 1.4 minus 1. So from here you will get the swept clearance volume as 27.079, or you can write as 0.027 meter cube. Since we know that clearance ratio is given as how much? 0.1. Since clearance ratio is 0.1, that is V1 by V2, that is Vs plus Vc by V swept clearance volume to that of swept volume. Sorry, my bad. Vc by Vs, and Vc you have got here. So this implies 0.1 is equal to 0.027 by V swept. So swept volume you got 2.7 meter cube. 2.7 meter cube. That was asked. Okay. Mean effective pressure now will be Pm into V swept is equal to work net. Put this swept volume. Pm into 2.7 is equal to work net was 1500. So mean effective pressure will come out to be 5.53 bar. Answer. Okay. Now they have asked cylinder ratio. Oh, sorry, cylinder dimensions. Third point. Pi by 4 d square L is equal to V swept. We know that. And since L by D is given to be 1.5 in the question, L is 1.5 times of D. Let's put 1. Pi by 4 into D square into 1.5 times D, and swept volume is how much? 2.7 meter cube is equal to 2.7. So from here, diameter will come out to be 13.2 centimeter and length will come out to be 19.6 centimeter. This is also your answer. Now, some of you may ask that why we have written this part. We have not used this part. Yes, we have not used, just to recap the concepts of thermodynamics. That if someone asks what is the work done by compression, what you will do, what work done from 1 to 2. If someone asks what is work done from heat addition at constant pressure, that will be 2 to 3. Expansion 3 to 4 individually if they ask. So you need to have all these values P2, P3, V1, V2, V3. Now you have all the values you can put and get the work done also for each and every process. You know the net work done, but you don't know the work done for each process. Any doubts in this question? Please ask. You should again revisit today's tutorial. It is very important because you will understand that a lot of concepts, detailed concepts have been done. If you have any doubts, you can ask me in the next session also. All these sessions are being recorded, and NPTEL team will send you the Google Doc sheet, as Santosh said. So where you have links for all the recordings as well as the Google Drive link where the PDFs are available, which I upload. If not, you don't get the email. The doc sheet will remain the same all the time, just with the updated links. If you still can't find it, you can search it from my YouTube channel. I'll write it here. The name of my YouTube channel is NPTEL with Varnit. My name is Varnit and I'm from IT Delhi. So this is my YouTube channel name. In the playlist section for this corresponding course, you can find out the videos, as well as in each video description, the link of the Google Drive is there, from where you can find out the notes of this lectures. Okay, as well as other subjects has also been available. So I'll suggest you that you should again rewatch the tutorials, complete your assignments. You should also watch the lecture videos, follow through that. Still, if you have any doubts, you can ask me in the next session at any point of time. And you can also share among your colleagues, batchmates as well. Okay. All right. So I think let's end this session here, and I'll see you next week, next Tuesday, same time, 6 to 8 p.m. Bye-bye.